we now look at how to construct confidence limits for a population variance. Now, since the random variable n minus 1 times the unbiased version of the sample variance, s squared, over the population variance has a chi-square distribution with n minus 1 degrees of freedom, it follows that the probability that this random variable is less than or equal to the upper alpha percentage point of a chi-square distribution with n minus 1 degrees of freedom is equal to 1 minus alpha. We can rearrange the terms in this event to get sigma squared on one side of the inequality by itself, and so this gives us the probability that the population variance is greater than or equal to this random variable, n minus 1 times the sample variance over the upper alpha percentage point of the chi-square distribution with n minus 1 degrees of freedom, that probability also being equal to 1 minus alpha. And so we can interpret this in terms of relative frequency probability, which would imply that in repeated sampling, the random variable given by this expression, again, n minus 1 times the unbiased version of the sample variance divided by the upper alpha percentage point of a chi-square distribution with n minus 1 degrees of freedom, will be less than or equal to the population variance sigma squared 1 minus alpha times 100% of the time. Hence, the variance sigma squared will be greater than or equal to that random variable, again, 1 minus alpha times 100% of the time. So the random variable that we're talking about here, given by this expression, is a 1 minus alpha times 100% lower confidence limit for sigma squared. Now, once we have our sample and have calculated the sample variance, and then from that calculated this lower confidence limit, the way we interpret this and what we say is that we are 1 minus alpha times 100% confident that the population variance is greater than or equal to that lower confidence limit. Now, similarly, the probability that we can think of this as kind of a standardized version of the sample variance, so n minus 1 times s squared over the population variance sigma squared. The probability that that random variable is greater than or equal to the upper 1 minus alpha percentage point of the chi-square distribution with n minus 1 degrees of freedom, by definition of this percentage point, is 1 minus alpha. And so then we can, again, rearrange the terms in this inequality to get sigma squared all by itself. And so this gives us the probability that the population variance is less than or equal to this quantity is 1 minus alpha. And so again, we can think of this in the context of relative frequency probability. And so this random variable will be greater than or equal to the population variance, sigma squared, 1 minus alpha times 100% of the time in repeated sampling. And so therefore, because of that, we can kind of look at this from the other perspective and say that the variance, sigma squared, will be less than or equal to that quantity, 1 minus alpha times 100% of the time. And so that random variable, n minus 1 times s squared, over the 1 minus alpha upper percentile, percentage point of the chi-square distribution with n minus 1 degrees of freedom, that random variable is a 1 minus alpha times 100% upper confidence limit for sigma squared. And again, once we have our sample and calculated the sample variance, and then from that calculated this upper confidence limit, we say that we are 1 minus alpha times 100% confident that sigma squared, the population variance, is less than or equal to this upper confidence limit. Now, if we compute both a 1 minus alpha over 2 times 100% lower confidence limit, which would be given by this expression here, and a 1 minus alpha over 2 times 100% upper confidence limit for sigma squared, and put them together, then what we have combined together is a 1 minus alpha times 100% two-sided confidence interval for sigma squared, And once we've constructed that, we say that we are 1 minus alpha times 100% confident that sigma squared is somewhere in this interval. Now let's take a look at an example. Again, looking at this example where we are filling jars with peanuts. And so again, in filling the jars with peanuts, we not only want the average weight of the contents to be 8 ounces, but we also want to maintain a degree of consistency in the amount of peanuts being dispensed into jars. If one jar receives too many peanuts, it will overflow and waste peanuts. If another jar gets too few peanuts, it will not be full, and the consumer of that jar will feel cheated, even though, on average, the jars have the specified amount of peanuts. Therefore, a test of the variance of the weights of peanuts should also be part of the quality control of the process. So with this in mind, suppose that the weight of peanuts in at least 95% of the jars is required to be within 0.2 ounces of the mean. Formulate and perform a test to check this and use a significance level of 0.01. So we've already done that test. We've already done the hypothesis test. And based on that test, we concluded that the machine was out of control for that particular situation. We rejected that null hypothesis. But suppose that we wanted to answer this question using the appropriate type of confidence interval. So the question would be, would a lower confidence limit, an upper confidence limit, or a two-sided confidence interval be the appropriate type of confidence interval to answer this question? And so we are to construct and interpret the appropriate type of interval. And so because the test is a one-sided test, we would construct either a lower confidence limit alone or an upper confidence limit alone. And because it was a right-tailed test, the appropriate type of confidence limit is a lower confidence limit. And then finally, since the test was performed at a 0.01 level of significance, the confidence level that we will use in order to be consistent with this hypothesis test is a 99% lower confidence limit. And so the formula for the lower confidence limit would be given by this expression here, n minus 1 times the sample variance over the upper alpha percentage point of the chi-square distribution with n minus 1 degrees of freedom. And so we have that calculation here. The 99% lower confidence limit for sigma squared, the variance of the population of fill weights, is given by this expression. And so we see here, remember that the sample size is 16, so we have 15 degrees of freedom. And the upper 0.01 percentage point of the chi-square distribution with 15 degrees of freedom, we found to be 30.578, looking that up in the chi-square table in the context of that hypothesis test. And so the 99% lower confidence limit for sigma squared is 0.0156. And so what we can say then is that we are 99% confident that sigma squared is greater than or equal to 0.0156. And since 0.0156 is greater than 0.01, we can conclude based on this lower confidence limit that sigma squared is greater than 0.01. And because it's greater than 0.01, we conclude that the machine is not in control in terms of the variability of fill weights, and therefore the machine should be shut down and adjusted. And so that is how we can use a lower confidence limit to answer the same kind of question that we can answer with a right-tailed hypothesis test. And not only can we answer that qualitative question, but we actually get a little bit more information regarding these specifics, or at least quantitative information regarding the value of sigma squared. We're 99% confident that the sigma squared is at least 0.0156. So that gives us some additional information above and beyond the kind of information that's provided by the hypothesis test. Again, not only using a confidence interval, not only can we answer a qualitative question like we can with the hypothesis test, but we get additional information about the range of plausible values for the population parameter of interest. And so that wraps up this discussion of inference procedures for a population variance. In the next section, next lecture videos, we're going to be looking at inference procedures for a population proportion.